Thank you. So my name is Hitesh Tiwari, and I'm from Trinity College in Dublin. And I guess my research areas are network security and applied cryptography. And we've been working in the blockchain space for around 10 years now. So during the pandemic, we kind of looked at this whole idea of COVID passports. And we were thinking, well, how do we put these COVID passports onto a blockchain in an anonymous manner? So this work has kind of came out of that, and this was done kind of a couple of years ago. So we actually haven't done started a real project with UBRI yet, and that's going to happen in the next few months. So I kind of thought, well, maybe what I'll do is I'll give you some background about what we did previously and an overview of the sort of stuff that we've been doing in Trinity College in the area of blockchains. So this project was called CoviChain. And what we wanted to do was to build a system that was based on biometrics and some knowledge that you know of to create an identity on the blockchain. So let me kind of dive into this a little bit. So the motivation was that we wanted to store vaccination records of all individuals on the planet, right? So a really, really big database. Right, that was the one big challenge that we wanted to look at. The second was that we wanted everything to be anonymous, and it had to be publicly accessible, right? And we wanted to, of course, put it onto a digital ledger or a blockchain. So this ledger would act as your global passport. You could travel to any part of the world and then somehow identify yourself on a public blockchain and then be able to identify that you had the correct vaccination required for that jurisdiction. So you could move from one place to another without having to carry anything with you, just your own identity, which is part of your physical self and some knowledge that you possess. So that was kind of the motivation for this thing. So the project, as I said, was called CoviChain. And the key features was that we didn't want to have off-chain data in this. So we wanted to kind of store everything on-chain. And because it was a vaccination passport, the amount of information was small enough that we could actually put it into let's say a transaction on a Bitcoin blockchain or Ethereum blockchain, right? The other thing was that, again, we didn't want to have it to be online all the time. So we wanted to have a situation where if you had no internet connectivity, we'd still be able to register you on the system. So, remote places where you may be doing vaccinations, but you don't actually have an internet connection on the field. So we'd like to kind of be able to do this on the field without any connectivity, and then at a later point, upload all the data onto the blockchain. And a bigger requirement was that we wanted no hardware. Right, and that's a big ask, right? We wanted to have no cryptographic tokens, we wanted to have no QR codes, no smart cards, none of that sort of stuff, because most people don't have access to that, right? So we wanted this to be a very, very simple system. So that was a big hard ask for us here. And then we wanted no GDPR requirements. Of course, no personal data on the blockchain at all. Nothing that could identify you unless you wanted to identify yourself to others, right? So no PII on the blockchain. So a lot of asks that we had for this particular project. The advantages, of course, is that, now you don't need to carry any sort of paperwork with you, no sort of digital certs. It's all there on the blockchain. Once you identify yourself, well, then we can find you on the blockchain. Again, because of the nature of the blockchain, there was no administrative authority that was going to take charge of this. This was a distributed system, so multiple people would add records to this blockchain. So it would be no single point of failure and then high level of transparency, of course, right? Everybody can see what there is on the blockchain. They can kind of make sure that whatever records there are correct. And then finally, of course, you as the user had control over who you show your records to. Unless you show your biometric or you combine your biometric with some information that only you know of, you could only then create the identity to be able to find yourself on the blockchain. So the system design, the way we did this was that we wanted to make use of two-factor authentication, right? So some requirement of that something that you have and something that you know. So some physical identification of yourself and something that you know of. Now, the something that you know of, we chose very carefully here. We chose things like date of birth, gender, country of birth, things that you could input programmatically into the system. So something that you didn't have to type. So I didn't want to use a name or a surname, because that is something you type in and you can make mistakes. So these are sort of things you can just have pull down menus of and just enter those things in. So very little room for error. And then, of course, something that you possess, either let's say a fingerprint or an iris scan, right? So that was the biometric end of things. So that's kind of, we wanted to kind of build these, take these two things and use this two-factor authentication mechanism to build an identity for you. Okay, so so let me go forward. So the blockchain was, of course, part of this, and that's used to store and access the records. At that time, we used Ethereum, as that was kind of a system that had lots of support, an API there. Could have used anything, really. And then what we wanted to do is that the records were to be publicly readable, so anybody could read the record, but only institutions that were kind of part of the system would be able to add a record to the system. Okay, so we use this sort of proof of authority sort of mechanism, consensus mechanism, and a round-robin way to add blocks into the system without actually having to do any sort of huge amount of consensus work in there. So that was the kind of the blockchain structure. Now let me kind of show you how this whole thing works, right? So this is kind of the main thing. So we have a blockchain, and what we want to do is that you could imagine a situation where in a university setting, you could go up to an office in your university and get your iris scan, right? So we use iris as our mechanism to be able to do the biometrics. So you get your iris scanned, and then we take a hash of that iris, right? And that hash is stored somewhere randomly on the blockchain. Okay, and that could be done for every user in the university that you're in. And you can imagine we replicate this along a global scale. And at some point, you might go to some health center and get an injection for your COVID. And what we do is that we'd store identity for you along with your COVID vaccination details. Now, the way we created that identity is an interesting way of doing it. So what we do was we take a hash of your date of birth, concatenate that with your gender and your country of birth, and concatenate that with the hash of your iris scan. Okay, now the eagle-eyed amongst you will see that there's H1 and H2 there. So there's two different hashing algorithms that we're going to use here, right? And there's a good reason for that. So imagine that this iris scan hash was taken let's say in some facility in your university, and at a later date when you want to prove yourself that you have a vaccination passport, you may actually get that iris scanned at an airport or some other facility, right? So there's going to be maybe some differences in the way the iris is captured in each case. So that's why we have this kind of different sort of hashing algorithm for the scanning. So H1 is not a traditional hashing algorithm, and I'll come to that in a second. H2 is your traditional hashing algorithm. So the ID is created by taking a hash of something you know and something that you possess. Okay, and that gives you your ID. So we store these randomly across the blockchain, right? So these are stored at some random interval, and these are stored at some random interval. So there's no correlation between the two. Okay, sorry. So going back to this hashing, right? So traditionally, a hash function has something called the avalanche effect. You change one bit in the input, and up to 50% of the output should change, right? So that's the traditional hashing algorithm. But what we used here for hashing the biometric data was a locality-sensitive hashing mechanism. So as you can see here, we've got two strings which are exactly the same. And using our LSH mechanism, the similarity between the two outputs is exactly the same, right? Whereas here we've got two strings which are slightly different. So instead of quick, we've got quicker, but we don't have a totally different hash coming out. The similarity between the two hashes is 0.92, right? 92%. So there's a slight difference because the input strings are different, but they're not radically different. Now, if you use the traditional hashing algorithm, this would be totally different to what you see here. Right, so we use that for our hashing. So just going back, so H1 is the LSH version of the hashing algorithm. H2 is our traditional SHA-256 hashing algorithm here. Okay, so this is how the algorithm works then, right? We capture your date of birth, we capture your gender, your country of birth. We also capture your biometric scan. And then what we do is we create a hash of the feature vector of your biometric scan using our LSH algorithm. And then what we do is we go through the blockchain. Right now, the second time, anytime we capture your biometric hash algorithm, it may not be exactly the same as the first time. So what we're going to do is we're going to go through the hash chain looking for H1FV and matching things which are very close to it within some threshold, let's say 90%. Okay, and so we're going to get a set of these matches that we have there. We're not sure which one is ours. We think one of these might be ours. So what we do is that for each person, so this should be ID hash as opposed to H2 hash, we're going to ask you to input your date of birth, gender, and country of birth, and then we're going to match it with one of those hashes that we found on the blockchain. If we find your ID, then we know it's an existing user. Okay, and we retrieve your record from the blockchain. If for some reason we find that you're not on the blockchain, we've exhausted all of these in the set, then what we're going to say is, okay, well, you're a new user. We're going to add your biometric hash, your biometric scan on the blockchain, and at some point later, we're going to add in your vaccination record. Okay, that's kind of the way we did this, right? So there's no personal information stored on the blockchain. You can't go back from the hash of the biometric to the actual biometric itself. Once that's been captured, we just destroy that biometric information. We don't keep that ever again. We don't keep any of the things like your date of birth, gender, or country of birth on the blockchain either. So nothing is stored on the blockchain apart from, let me just go back, your hash of your biometric, and at some point later, a transaction which shows, which captures your ID, which you capture that way, and your vaccination record. Okay, so what was that? Oh, yeah. So as I said, we need to perform some heuristic matching here because of the fact that whenever we take your hash again, it's never going to be exactly the same as the first time around. So we're going to use that LSH mechanism to find a bunch of hashes there which are closer to yours and then try and create your ID. We implemented this using a number of nodes. We did some testing with all of this sort of stuff. So we had an ILS template extractor from an existing open source project. We took those images that we had from a data set, created a bunch of hashes out of those biometrics, put them onto the blockchain, and then tried to do some testing to make sure that this thing actually worked the way we thought it might be working. So 3 important metrics we wanted to kind of validate here was how accurate was the system, right? When we're locating these records. How quick was the iris extraction process? Around 1.5 seconds is what we kind of saw. And then the speed and efficiency of the blockchain as well, right? So these are the sort of things, if you're gonna have a massive blockchain with everybody on the planet's record stored on it, well, these sort of things matter to us a lot. Right, and we kind of use a bunch of data sets out there that were out there already, and we cleaned them up a little bit because there were quite a lot of entries which were duplicates or which we just couldn't use, and then try to run our system on that. So as you can see here, right, so the matching accuracy was pretty good, right? It's around 90% in most cases. And again, the time to extract out these irises was pretty low, right? We're talking less than a second in most cases. So pretty efficient in the way we did this. Now, of course, the number of records we started off with, the number of records we use is quite low because there was quite a number of those that we just weren't good enough for our purposes. Okay, security considerations of this then, well, you can have offline attacks, right? When all of this data is there for anybody to kind of sift through at their leisure, of course, there's lots and lots of people who will try and kind of extract out sensitive information out there. And the more personal information you use, such as your, your surname and things like that, or your country of birth and date of birth, all of those things together can somehow be pieced from the internet again, and maybe used to try and kind of locate you on the blockchain. So the less personal information you use, the better, but of course the entropy there becomes less as well. The other thing we did, that we took the LSH mechanism and we made it a bit more stronger. So we created something called the S3 hash, which is a variant of LSH, where we were able to make sure that it was input hiding, i.e. nothing that you input into it could be gleaned from the original data. So you can't go back. It's a one-way function, of course, right? So we did that as well. Okay, so this is kind of a good way to store vaccination records anonymously on the blockchain, right? And what we used here was biometrics and a special hashing technique called locality-sensitive hashing. And the thing is that this could be used for other applications. This is the important thing, right? You don't actually have to store just biometric information or your COVID-19 passport information. You could store all your healthcare data on this. Right, that's the important thing about this sort of thing. But of course, if you're kind of store things like, let's say, MRI scans, CT scans, you don't want to store that on the blockchain because that's just going to, kind of bloat it too much. So in that sort of situation, what you'd want to do is to clean out all that data, make it anonymous, and then store it onto IPFS if you wanted to. Right? But the same thing in order to locate your self on the blockchain applies. The identity mechanism still remains the same. You still use the biometric and something that you know. And you can have multiple instances of yourself on the blockchain, right? So you can have multiple IDs belonging to you on the blockchain, and as you go through it and you find yourself, you can extract out your whole lifetime medical history if you so wanted to. Okay, so that's kind of where that was. So I got around 2 minutes. What I wanted to do was just kind of leave you with an overview slide of the sort of stuff that we've been working on in Trinity. So as I said, we kind of did some work on identity management and blockchains, or biometrics. The other thing that we kind of did back around 10 years ago or 8 years ago is this idea of creating a PKI, right? What we wanted to do was create a PKI at zero cost to the user. And again, the way we thought about that was, well, you know what? Your institution knows about you, so they can identify you. If they could act as a subordinate CA, they could issue a cert to you. So imagine that everybody in your university gets a cert from their university, everybody in my university gets a cert from my university, and we put all those certs on the blockchain, right? And suddenly we have a PKI. If you have a PKI in place, you can do lots of good things, right? So one of the things we thought was, well, you can actually have secure email. Today we kind of exchange very sensitive documents with each other without ever encrypting them. But if you had public keys of people on a blockchain, well, you look up that public key and encrypt the data towards that person using that public key, right? They could decrypt. We also looked at DNSSEC, which is a secure version of the DNS. And again, the problem with DNSSEC is that it bloats up DNS. And DNS, as you know, is a very time-sensitive thing that has to happen very quickly every time you go to a new website. So again, what we thought was, all that information that's required for DNSSEC can all be stored on a blockchain. Again, pull that off from there and then verify the identity. As I said, we kind of think about healthcare and managing your healthcare data lifetime on the blockchain. Again, you can put all that up on the blockchain using an identity mechanism to be able to pull all that data out at a later stage. Recently and currently we're doing some work on proof of work. So we kind of think of proof of work as being the most secure consensus mechanism out there. And what we want to think, the way I think of proof of work is that proof of work is like a 100-meter dash, right? There's 10 people running a race, only one person wins. Expend huge amounts of energy. All that energy goes to waste. Well, imagine yourself in that race, right? And next to you, you see there's Usain Bolt, right? Before you've got out of the traps, he's halfway down the track. You've lost that race. You're never going to win that race. You might as well give up at that point. So if you can see that happening, maybe you should move to another race where you might have a chance. So instead of having a single blockchain, maybe you can have multiple blockchains, starting at t is equal to 0, t equal to 1, and so on and so forth. If you can't win on the first blockchain, you move on to the second blockchain. and so on and so forth. And if you can see what other people are doing on the same blockchain and you're way behind, you move on to another one. And that distributes the mining power across the network, right? And increases the TPS. You kind of heard about ZK voting a while ago. Well, we wrote a paper on this in 2017. The journal paper and the conference paper together have more than 100 citations today. Right? Again, what we did was we took everybody who wanted to stand for election, gave them a wallet, and everybody who wanted to cast a vote would just cast a vote into the wallet of their choice. Okay? And that way, you'd have a first past the post voting system. As long as the total number of votes on the blockchain was less than or equal to what was issued, and again, you could kind of do that with your identity management system, you could have a voting system in place. We never implemented it, but it's there, right? I've been working on mobile network security, and we've developed a broker which allows us to share network bandwidth and bid on spectrum using a blockchain. Okay. The project that we're going to be doing for UBRI is building decentralized social media network. And that work is ongoing at the moment. And a lot of work that I'm doing currently is in the area of post-quantum and lightweight cryptography. Okay, that's kind of an overview of things, of what we're doing. Happy to answer any questions.
Awesome, thank you so much. Thanks for sharing the lots of great work that you're doing. I think we have time to take one question, if anyone has any question.
Is there anyone else?
Yes, there. You can give them.
Hi, I really like your project, paper. This is really cool. I had one question about, so like healthcare data is important for your whole lifetime. And like the hash functions that we have are computationally secure for like 10, 20 years. But there's a threat that, 40, 50 years down the road that these hash functions won't be secure anymore. Have you thought about that, or how do you grapple with that?
So we are kind of working on post-quantum stuff, right? So we're looking at various aspects of the blockchain in terms of the signature algorithms and maybe the hashing algorithms as well, and the consensus algorithms all together to make sure that the next generation of blockchains that are out there are quantum secure. So we are actually looking at that at the moment, and there is some NIST activity in this area in terms of already encryption algorithms and signature algorithms. Whether they've done work on hashing algorithms, I'm not sure. But yeah, absolutely, that's, like store now and decrypt later is a dangerous thing that we need to worry about now. So we are looking at that, yeah.
Yeah, so I'm just looking for a teeny bit of clarification. A few charts ago, you had some statistics about the accuracy of yeah, it's right in here. So searches perform. So this is actually a search algorithm and not a challenge algorithm?
Yeah.
So that seems to be like, first of all, a much more difficult problem to solve than a challenge algorithm. Mm-hmm. And so my first question is, why in the world wouldn't you structure this as a challenge problem instead of as a search problem? Because as soon as it's a search problem, at accuracies of 90%, as impressive as that is from a computer science standpoint, in terms of implementing a real world system that's pragmatic and affordable and, deals with the reality of people standing in an airport for argument's sake, arguing with people, that's nowhere near good enough to be pragmatic. So what was your thinking and your design point if you're really trying to implement this as a search algorithm? Yeah,
so again, we didn't actually think of this as a challenge, and that's a good way of thinking about it, and now that you mention it. The first thing as computer science guy would think is, can I just search the thing and get it, right? And that was the simplistic way of thinking about it. So, but yeah.
Challenge algorithms are much more common and pragmatic.
Absolutely, yeah. Now that you say it, yeah, it could be another way. But we never implemented this in any real world thing. But in a real world scenario, you may want to go with a challenge algorithm.